Oh, crap. Oh, there it is. Hi, Dylan. Be there in a second. Oh, crap. That one came out too. Ah. Sorry, Dylan. You there?
Yep. How about you?
I'm doing fine. Are you? Do you need some help with something? I'll be happy to do what I can. Okay.
Not so far. I think the most difficulty I had was just actually calculating the wavelength.
Okay. Okay. That's calculating the wavelength. That comes to, it's a simple equation. It's the speed of light is equal to the wavelength times the frequency. If you have the frequency, all you got to do is divide the the speed of light by the frequency. And then sometimes you got to change it into the correct label. But other than that, it's really a piece of cake.
I think what was happening is my calculator was one power of the 10th off.
Okay. Are you doing it with the E button, Dylan, or are you trying to do it with the parentheses?
With the E button.
I don't know what to tell you then. I'll get in there in 1 second. I just want to pop up the PowerPoint, and then I'll get in and we'll look at the quiz. Okay.
All right.
All right. Okay. Oh, somebody's bothered me. Oh, I've bothered me. Okay. All right. Was quiz 13?
Yep.
Okay. So. All right. We're doing properties and we're going to get to add edit questions. Okay. Which one were you talking about, Dylan?
I can't pull up my quiz.
Okay. I'm here. Are you seeing the screen?
Oh yeah, now I see it. 1 second, let me see. Let's try. Can you do 4?
4?
Yeah, because that one looks like I could use help with that one.
Okay, number 4. Okay. Basically, you have the frequency, right?
Yeah.
Okay, so if you have the frequency, you have the formula E is equal to H nu. Nu is the frequency. Okay. H is a constant, 6.63 times 10 to the minus 34th. So basically, all you do from this is you multiply 6.63 negative 34 times the frequency, 5.44 to the 15th. I do that math out, I come up with 3.61 times 10 to the minus 18th. Are you with me so far?
Yeah.
Okay, now that is the energy of 1 photon. How much energy does a mole of that photons have? So basically, you have to multiply this by 6.02 times 10 to the 23rd, and you end up with 2.17 times 10 to the 6th, which I think is the correct answer.
Sorry, my dog started barking.
Oh, that's okay. Believe me, I'd be surprised if my dogs don't start barking soon.
I did have one other question too for the pop quiz.
Yep.
Is there, it says essay responses. Do you just want like a paragraph or do you want like a essay?
I want an essay. Have you looked at it yet?
Yeah.
Come on, Dylan. Give me an answer, okay? I want you to go into some detail. I don't want you to write pages and pages, but go into some detail. I get a kick out of reading them, okay, Dylan?
Okay, good, because I don't
Hey.
have time for the essay.
Basically, Dylan, just give me what you can give me. All right. It's a free 10 points. I realize that some of these quizzes, especially the last one, were quite difficult. So every now and again, I give a pop quiz that is going to be fairly easy.
Okay, all right,
All right.
thank you.
No problem. So other than that, you're doing okay with this stuff? How about
I
the
think so.
how about the calorimetry problems?
They're more difficult, but once I sit down and actually look, like slow my thoughts down and actually look through them, I'm able to get through them.
Okay. On the test, don't be too slow though. I'm laughing, Dylan.
Sorry, I couldn't hear you. My dog started barking again.
Sorry, I said, but on the test, don't be too slow.
Oh, yeah, that's true.
Anything else you got?
I don't think so. I think the lab really helped.
It does. It did. I hope that the calculations I went through in the lab, I hope those slowed it down to a step-by-step basis.
Oh, yeah, it did.
And the other thing is, the more you practice this, the more you get it down, the better you're going to be at doing it. Okay?
I did try to find why you take 25 and divide it by the specific.
You did?
Did not find an answer yet.
I swear to God, I spent some time trying to research that. I could not come up with anything. So if you find it, God bless you.
It bothers me that there's no answer.
Except that Dylan, some things you just have to realize that this is proof that there is a God. Some things are unexplainable.
That's a good point.
Oh, now we're gonna get into the quicksand tonight. You ready for that?
Oh yeah, I'm excited for the next chapter, especially.
Don't be so. Have you ever gotten into Schrodinger's equation and Heisenberg stuff? Have you ever did you do that in AP?
No.
We're going to get into it a little bit. We're not going to get into it all that much. Have you looked at the videos that I put online? The online outline?
Watched those ones yet.
That's a good idea to start to understand it. The girl that does the Schrodinger equation is excellent. And she's cute to look at too.
Well, all right.
But does an excellent job explaining the Schrodinger equation. And she does it in a humorous manner. So I was entertained by it, but then again, I'm a chemistry nerd. What can I tell you? So what else is going on, Dylan? Where are you going with all this?
Biomedical sciences.
Okay, what exactly does that mean?
Eventually, I want to get to research and clinical.
Okay, that's great. Getting into biochem or the actual biology aspect of it.
Probably more biochem because I want to study the effects on drugs effects on us, I guess.
How good are you at computers?
I'm all right. I'm going to take a couple courses on it to get better though. Because
that's where it's all at right now, Dylan.
It really is.
When in 1980 to 1981, I worked as a synthetic chemist, which meant what I was doing was I was making drugs that were meant for use as high blood pressure medicine. And basically all we were doing is we were trying to imitate other drugs that were already on the market. And it kind of makes sense because if something works, then if you play with it around a little bit chemically, then maybe something else will work. Whole different ballpark now. Basically, they have the computer programs that how these things work. It's kind of like a key and a lock situation. One thing is the key, it will fit exactly into a like an infection. And it will key in there and lock into it. And once it locks into it, the body can then get rid of it. But it has to be the right shape and it has to have the right charges on it. What they're doing now is they're simulating these things with computer programs, which is absolutely amazing. That's really, if I had to do a field trip, Dylan, that is really what I would love to see. I would love to
That would be
see.
amazing.
I'm sorry, Dylan?
Would be amazing.
Yeah, I would really love to go in and just watch them and just how they simulate these things to try and come up with a new drug that will possibly work. And it's like these vaccines, Dylan, that they're pulling out for COVID. Man, the speed with which they're going through this thing is utterly amazing to me.
It really is, especially, I mean, even compared to flu outbreaks, how fast they're getting these vaccines through is crazy.
Yeah, absolutely. And so that is a field trip I'd love to take. So how much further do you have to go? Where are you planning on going with this? UF or?
I think I'm going to go to UCF.
Okay. Because I know UF has a dynamite biochem program.
Really?
Yeah, I interviewed there for grad school at one point.
I'll have to look into that then.
Just something to thought. Yeah, it's just something that's I'm throwing out there. But that's absolutely fantastic, Dylan. I get a lot of students that they give me the pat answer. Oh, I want to be a doctor. I'm going to be a nurse, or I'm going to go into pharmacy. And it's like, man, guys, don't you know there's a whole world out there? Why don't you do something that's interesting rather than taking and counting pills out of a bottle?
Yeah, I want to be an innovation. I want to be discovering the new things.
And Guy, if you can be interested in what you're working at and getting paid for it, you got the tiger by the tail, man. That is the life. And as long as you're making enough to live on, hey, it's amazing. The most I ever made as a forensic scientist, I think it was $72,000 a year, Dylan. And if you watch what you're doing, I mean, I'm 63 now. My house is paid off. I got investments. My wife and I have investments that are well over 250,000. So, man, it doesn't take that much. Just even if you're getting paid a livable wage like that, and you will, if you're going into the areas you're going into, that's probably you'll probably top out at six figures, Dylan. Have you looked into salaries there?
Yeah, but that hasn't been my main motivation. I would like to have the money, but it's something that I'm actually interested in and that I want to do. So it doesn't matter as much.
Well, as I said, man, if you can get something you're interested in and you get paid for it, it is absolutely wonderful. Blake's in. No, that's absolutely fantastic. Why UCF?
I don't know. I'm from Ohio, and that just since I've moved down here, my original school was Rollins College in Winter Park. And then I decided that I wanted something bigger where I could branch out and make more connections.
Uh-huh.
And they also have a lot of scholarships and professors that are doing experiments of their own and things like that.
Yeah, that's where it's at. I mean, once you get in, literally start to figure out who the professors are. And once you do that, find out what their research is and take it seriously, because who knows, you might end up getting your name on a paper.
And that's big just coming out of college.
Yep, absolutely. Blake, Ian, how we doing?
Good. How are you?
Doing
Hey, hey.
fine. Hey, Blake. Blake, are you doing things? Are you doing okay? I'm sorry, Ian. I'm not throwing you under the bus or not forgetting you, but
All good.
we did speak earlier. Blake, how are you doing with this stuff?
Yeah, it's not bad.
Okay. It's not bad. It's better than where I thought we were going. It's not
Yeah.
bad. It's encouraging to me. Okay.
Cool.
Just look at them. They're really and truly, they're not hard problems. No, I'm not going to say anything about Chem 2. I like to make the inference that in Chem 1 differs from intro. In the intro, you're walking out the front door. Chem 1, you're jumping off the roof. Chem 2, you're jumping off the 5th story. And the reason I say that is because right here and now, we're giving you the equations and you're just popping in the numbers to fill them out. You just have to make sure that you get the right numbers in the right place. Chem 2, what you do is you have to manipulate the equations to get the equations to where you need them. Then you start to pop in the numbers. It'll be explained to you. Believe me, trust me, it will be explained to you. Okay, we got about 5 minutes to go here. Anybody have any questions, Blake?
No. Mm-mm.
Nothing?
Not at the moment, no.
Have you finished your pop quiz, Blake?
I have not.
Have you looked at the pop quiz?
I have not.
Oh.
It's
better
not due
hurry-
till the 25th, though, right?
Yeah, but there are essay questions, Blake.
So they're going to take a while. Okay, thanks for the heads up. That's right.
At least look at it. Then decide
do.
whether you're going to start right away or not. Ian, have you started the essay? Have you started the pop quiz yet?
No, but I'm looking at it right now.
Oh, you are, huh? Don't ruin Blake's surprise.
Can I open it without it closing out on me? Like, does it have a time limit?
I don't believe it does. I can actually go in there right now and tell you. Since nobody has any questions for me.
It's unlimited. I got it.
Ah,
My
okay.
computer finally loaded.
Okay. Good enough. So spend as much time as you want on it. I actually, believe it or not, I do read everybody's responses. And I usually get a kick out of 1 or 2 of them. Oh, I'm tap dancing here, guys. Blake, what are you doing? What are you planning? What are you going to do for the rest of your life, Blake?
Computer science.
So why are you taking
Programming.
chemistry?
It was this or physics.
Good choice. At least you have me to entertain you, Blake.
Yeah, we laugh in the background. You just can't hear it.
Okay. Good for you. Good for you. How about you, Ian? What are you going to be when you grow up?
I'm undecided at the moment, but FWC seems pretty interesting at the current moment, I would say.
What's FWC?
Florida Fish and Game Officer. Pretty basic. You only need an AA though, so it's not nothing special.
Hey, Hey, those guys do bust their ass. And is that what you'd like to do? Just being out in the wild?
Yeah, I mean, I've been big on it. I was in Boy Scouts and I'm an Eagle Scout, so I was kind of
Mhm.
around it for 18 years. But it just would be interesting. I want to be a cop, but with everything going on, that's the last thing I'd probably want to do.
Yeah. Yeah, just understand, Ian, that there are hierarchies when you're dealing with cops.
That is very true.
Believe me, I've dealt with enough of them. Oh man, it is amazing. The egos that can get in a room are absolutely phenomenal. And if the FBI gets involved, God help us all. All right, guys, I got 3 of you here. One person's already been through this lecture.
I'm gonna grab my dinner, so don't call on me for like 10 minutes.
Was it Ian?
Yes.
No problem. No problem at all. I got about a minute and a half till 5:30. Do you mind if I get in and start reviewing this stuff?
No.
Yeah, sure thing.
Okay. All right. Basically, the whole history behind this aspect of chemistry / physics, because right now we are at the interface between chemistry and physics. You go too much further and we are talking pure physics problems. Right now, we're just dealing with the chemistry of it. What you have to understand is that at the turn of the 1900s, they thought everything was done. All the big chemists thought, hey, we've discovered everything. There's nothing more to discover. As a matter of fact, we have explained everything. Then what happened is there was a couple phenomena that couldn't be explained. And it was because of this that some scientists, some chemists and physicists started to question whether the wave theory was in fact the end all tell all of the theories. So basically what happened is there started to be a big push around the turn of the century. We had those people that were stuck absolutely in their heels saying wave theory, wave theory, wave theory. And you had the other bunch who were just starting to bring up this, well, it's not really waves don't really explain everything. So it must be a particle. And you literally had these 2 factions coming to blows. So we have to look at the problem from both a wave aspect and a particle aspect. And basically the way we would define waves, we define them by a wavelength, which is the distance between the crests, and the amplitude, which is the distance from the axes that the wave is moving away from versus how high the crest is. Now, if we're dealing with wave theory, energy is related to the amplitude of the wave. And this kind of makes sense. It's the reason that tsunamis do so much damage. It's the fact that that wave is so high and has so much power that it wipes everything out as it hits it. So according to the wave theory, energy is going to be related to the amplitude. But for the particle theory, the energy is going to be related to the frequency. How many times this wave goes past a given point. So that is basically where we're at in this explanation. And what you have to understand is, and this makes a whole lot of sense, if the wave is longer, fewer of those waves are going to pass a given point if they're traveling at the same velocity. So if we have a small frequency, we have a long wavelength. If we have a large frequency, we have a short wavelength. So greater the frequency, greater the energy. So in other words, if I have a long wavelength, it's going to be low frequency, low energy. Short wavelength, high frequency, high energy. Now, if I'm dealing with light energy, electromagnetic energy, no matter what energy we're dealing with, frequency times wavelength equals a constant. If we're dealing with light energy, that constant is the speed of light. So this is one of the equations you really, really need to know. Speed of light is equal to the frequency times the wavelength.
Professor,
Yep.
we can't see your screen.
Geez, you could have gotten, I should have gotten into it.
I thought you were just reviewing off the top of your head, not from the PowerPoint.
Thank you. Okay. All right, so this is one of the equations you're really going to have to know. No, this is the equation that will convert frequency to wavelength or wavelength to frequency, because the speed of light is a constant, 3 × 10⁸ meters per second. If we know frequency, we can divide the frequency into the speed of light and get the wavelength. Same thing if we know the wavelength lambda, we can divide the speed of light by lambda, get the frequency. Now, when we're dealing with electromagnetic radiation, there are different categories for it. And you can look at the different categories as being either having more energy or less energy, small wavelength, high wavelength, large frequency, short frequency. It goes in this order: gamma rays, shortest wavelength, highest energy, highest frequency. Radio waves, longest wavelength, shortest frequency, smallest energy. And it goes gamma rays, X-rays, ultraviolet. Then we get into the visible region. In the visible region, you have to kind of like go the opposite of Roy G. Biv. Violet has the most energy. Violet, G. Biv. Indigo, blue, green, yellow, orange, red. Goes in that order in terms of energy. Then we go infrared, microwaves, radio frequency. Just like the quiz, guys, you're going to have to know what is a lot of energy and what is no energy and how this relates to frequency and wavelength. Basically, same slide. Now, what this means to you is if you have something like infrared light has the ability to stretch bonds out, to take those bonds and rotate those bonds. It has that much energy. It does not have enough energy to break the bonds. Microwaves, what they do is they cause molecules to rotate. And when they rotate, they create friction with one another. And this friction is actually what's causing your food to heat up. On the other hand, if we get all the way to ultraviolet rays, that's when we start to get into danger. Ultraviolet rays break chemical bonds. So when you're sitting out in the sun for long afternoons, like, I mean, dear God, I can show you my hands. I've gotten all kinds of cancerous things removed from my body because of the fact I stayed out in the sun too much when I was younger. So that's where that's going. Now, if we have a different type of radiation, we associate a different label for our wavelength. If we're dealing with ultraviolet, we like to talk about nanometers, which is 1 meter is equal to 10 to the minus, or 10 to the minus meters is equal to 1 nanometer. If I'm dealing with infrared, I'm dealing with micrometers, which is 10 to the minus 6. So this is just put in there. You don't have to memorize these. I'll give you the conversion factors, but it's just a good to know slide for you. Did I do these problems the other day? Did I get this far or not?
Yeah.
All right, these problems are fairly easy. Calculate frequency with the wavelength of such and such. The only hard part about it is you have to realize that the speed of light is in meters per second. So you have to convert the nanometers to meters and then divide that into the speed of light. Same thing here. In this case, I'm going to take the speed of light and I'm going to divide it by the frequency. If you need to have those gone over again, let's see, Joe, Blake, are we doing okay with this?
Yeah.
Joe,
Very simple.
Yeah, I
we're doing
reviewed over
okay?
this- Do the quiz I reviewed over this.
Okay, good. That's, believe it or not, silly me, believe it or not, that is what the quiz is supposed to be designed for. All right. We're all doing well with this wave nature thing until we get to start to study some things. Has anybody ever seen the Westerns where the blacksmith throws the horseshoe in the forge and really heats up that forge? And you take the horseshoe out and it kind of glows, doesn't it?
Yeah.
Wave theory can't explain this. Wave theory can't explain why the horseshoe is glowing orangish red. It took a guy by the name of Max Planck, and he did this around the first decade of the 1900s. And what Planck said was, if we think about energy, not in terms of waves, but if we think of it in terms of quanta, little packets of energy, then we can explain black body radiation. And basically what he said is that when something absorbs energy, it's going to absorb a certain amount of energy. And when it goes back to its ground state, it's going to give up that certain amount of energy. Einstein refined this. Einstein came up with the equation E is equal to h nu, where E is equal to the energy, h is a constant, Planck's constant, 6.63 times 10 to the minus 34th, and V is the frequency. Now, the best way I can think about this, has anybody visited the Guggenheim Museum in New York? Anybody know what the Guggenheim Museum is? Has anybody ever seen a painting?
Yes.
Yes.
Okay, all right. If you ever go to New York, the Guggenheim, just for its architecture, is absolutely wonderful. You can either start at the bottom floor and walk up, or you can start at the top and work down. And what it is it's a spiral staircase that kind of goes around the edge of the building. And as you're going around, if you're on the opposite end, you can look across the way and see the artwork from a proper distance. And in any case, it's one big ramp. So if we're thinking of wave theory, we're actually thinking about something that looks like a ramp. When you're in a ramp, you're walking up steady. You're having a steady energy to get from the bottom to the top of the ramp. All right? When I'm thinking quanta and quantum mechanics, I can't think of that steady going up It's like when you're walking up a ramp, you're not going to actually go in the same step. So you may use different amount of energies as you're walking up that ramp. On the other hand, if I have a staircase, I have a certain 6 inches that I got to lift my leg up and put it onto that stair and push myself up to go to the next stair, which is another 6 inches. The energy I'm expending comes in spurts of those 6-inch height differences. That is the basic difference between wave theory and particle theory. Now, if we know the wavelength of light, we can calculate the energy. Because, guys, we have 2 equations. One of those equations relates the wavelength to the frequency. The other one relates the energy to the frequency. So if I have the wavelength, I can take my speed of light divided by my wavelength. That will give me my frequency. I can then multiply my frequency times Planck's constant and get my energy. Or in other words, if I want to try and do this, let's see if I can do it. What I'm talking about. Okay, good. Good God, what happened there? Never mind. Sorry. What I was going to do is I was going to make a new equation out here where energy is equal to hc divided by lambda. And all I've done there is translate the c divided by lambda is equal to nu. Now, Planck was all well and good, but he had some people that were beating down this radical theory. And he basically lost all confidence in it until Einstein came back, and he basically proposed that light can have both a particle and a wave nature. And he explained this through something that he had called the photoelectric effect. By the way, ladies and gentlemen, gentlemen, Einstein did not win his Nobel Prize for the theory of relativity. He won his Nobel Prize for the photoelectric effect. All right. The photoelectric effect. Basically, wave theory cannot define it, because when wave theory goes into defining energy, it defines it through the amplitude of the wave. Well, what they found when they were doing experiments, they had waves with very, very high amplitudes, but a very, very low frequency. And these had no effect. When these would hit a piece of metal, this would not eject electrons. But on the other hand, they had some waves that had a small amplitude, but a high frequency. And these would hit the metal and they would eject the electrons. And they found that no matter what the intensity was, there was a minimum amount of frequency that they had to exceed in order to eject the electrons. And basically, this is what the photoelectric effect is. And basically, Einstein said, okay, the light was made of little packets of energy. And the energy equaled Planck's constant times the frequency. Basically, what he said was, low frequency light doesn't eject the electrons because no single photon has the energy to do it. But although this explained the photoelectric effect, there are other phenomena which occur that the wave theory works for, but the particle theory doesn't. So Einstein is thinking there's got to be some wave nature to this and some particle nature to it. And eventually he came up with the fact that he could figure out what the mass of a photon was. He knew that the energy was equal to h nu, or hc over lambda. And he also knew that the energy was mc squared. So if he substituted mc squared into the Planck's equation, you can get the mass of a proton, where it's equal to h over lambda c. Okay. Calculate, Dylan. We're going to set this up. Calculate the energy of a photon. A photon of energy with the frequency 7.3 times 10 to the 15 hertz. Do you have an equation, Dylan, that will relate frequency with energy?
Yes.
What is that equation?
HV or HC divided by lambda.
Yes. But Dylan, we don't have lambda here.
So HV.
HV. So basically, my energy is going to be my constant, 6.63 times 10 to the 34th, negative 34th, times 7.3 times 10 to the 15th. That will give me my energy in joules, because the label of Planck's constant is joules times seconds. The label of frequency is seconds to the -1. Okay, Blake. We have a wavelength of 720 nanometers. Calculate the energy. Do we have a way to turn wavelength into frequency, Blake?
Yes.
How do we do that?
Is that the equation C equals something times V?
A lambda.
What is that? Lambda. Okay.
Lambda is the wavelength. But in order to do that, do you have to do something with the nanometers?
Convert it to meters.
Yes, because the speed of light is meters per second. So you convert the 720 to meters. That would be 7.20 times 10 to the -7th. And you divide that into, or you multiply that by Planck's constant. And wait, that doesn't, no, let me back up, sorry. You calculate, you make the nanometers into meters, and then you divide that into the speed of light to get the frequency. Then you take the frequency and multiply it by Planck's constant to get the energy. Okay, makes sense, Blake?
Yep, sure does.
All right, but we have to understand, how many photons are we talking about?
Would it be one
Just one.
or? Yeah.
So if I want a mole of the photons, what do I have to multiply this number by? If I want a mole's worth, this is the joules per one photon. If I want a mole's worth of photons, what am I multiplying it by?
Avogadro's number.
By Avogadro's number. Okay. We can also do the problems in reverse. If we know the energy, we can calculate the wavelength. Because energy is equal to h nu, We can divide the energy by h, and yeah, divide the energy by h. That will give us the frequency. We can then take the frequency and divide it into the speed of light, and we will end up with our wavelength. I did it a little bit funky here, I realize. Here I use the equation E is equal to hc divided by wavelength. I solved it directly rather than going through the frequency. Are you all good with this, or did I just confuse the snot out of you?
I think
Yeah,
I'm
no, I
good.
get it.
Okay. Now, there's another phenomenon that gets noticed. And that is when you put a gas at low pressure and you subject it to a high voltage, what happens is it gives you different colors of different wavelengths of light. Wave theory would predict that you would get a rainbow out there. But we're not. We're getting simple line spectra. So if we do that, if we put a amount of gas into a low pressure light and then we ignite it, we get lines that look like this. From 400 to 700, hydrogen will give us 4 lights. Sodium basically gives us 2 very, very close to one another. So we are not getting a rainbow. We're getting very, very distinctive patterns. Which brings us to Niels Bohr. Did you all have the Bohr atom explained to you?
Yeah.
Okay, Blake or Joe? Ian, I know you had it earlier.
Yes.
Do you know what the Bohr atom is?
Yes.
Joe?
My bad, it's me. I can't remember it. No, I think so.
Okay, basically, Bohr saw these lines. And what he came up with was, okay, if there are lines here, then there must be very distinctive energy levels that an electron can occupy. Because if we're adding energy to that electron and it goes up to another level, as long as we're putting that energy in, it's staying at the higher level. We take that energy away, the electron wants to go back to its normal state. But it had a higher energy, it's going to a lower energy, it emits a certain frequency of light. Now, wave theory would have predicted that you would have a rainbow, but we're only seeing one particular wavelength of light. So what this is meaning is that there is a very distinctive energy level to where the electrons are, so that the electrons can only exist in certain orbits floating around the nucleus, much like the solar system is. And so we have our nucleus way down at the bottom. We have our first, if we're looking like a segment, an arc from the nucleus, we have our first energy level, our first orbital. Then we have our second one, third, fourth, fifth, sixth, and so on. Now, what Bohr suggested for these line spectra was we were putting energy in. The electron, say, was here. We would put it in, so maybe we'd excite it to the third energy level. As long as the energy was hitting that electron, it was staying in the third energy level. We take the energy away, that electron falls back to its original ground state, And when it does it, it emits a certain packet of energy, which is related to the difference between the two orbitals. So the Bohr model says that there are only certain orbitals that an electron can exist in. It can exist in these, and so it won't spiral into the nucleus. And as energy is absorbed or emitted, it will only allow you to go to other orbitals that are permitted. And Bohr's theory was borne out by some high school teachers. They were sitting around playing with numbers, and Balmer came up with the original formula. Later on, it was perfected by a guy by the name of Rydberg, and it's his equation that we're using today. And what Rydberg said, the change in energy from one orbital to the other is equal to negative, when you get to do something good, you get to name constants after yourself. So the energy is equal to minus R, which is the Rydberg constant, times 1 over the final orbital minus 1 over the initial orbital. Both of those are squared. Now, remember, if we're going back here, remember, we've excited the electron to the third level, right? It has gone, it had more energy, it gave up that energy to come to the first level. Is that exothermic or is that endothermic?
Endothermic?
If you're losing energy, if your system is losing energy, and the system is the electron, the system loses energy. Is that exothermic or endothermic?
Exothermic.
So what's the sign?
Negative?
Negative, which explains why there is a negative sign out here. All right? That explains why there is a negative sign here. Now, let's think about this. Okay? We're going from a higher orbital, so my initial number is going to be bigger than my final number. Is this going to be, is this portion of the equation, the 1 over nf squared minus 1 over ni squared, is this portion going to be positive or negative? Let's think about it. Remember, we said the initial is going to have a higher number, right? Because we're going from an outer orbital down to an inner orbital. The initial is going to have a higher number. So Dylan, say we have the thing going from the third orbital down to the first. So my NF is 1. My NI is 3. So in effect, this equation becomes 1 over 1 minus 1 over 9. Is that going to be positive or negative? Dylan, come on.
Hold on. I don't know why this is tripping me up.
1 minus 0.111. Is that a positive number or a negative number?
Positive.
Positive. Okay. Let's say we go from the fourth down to the second. So this portion of the equation becomes 1 over 2 squared, or 1/4, minus 1 over 4 squared, or 0.0625. You get 0.25 minus 0.0625. Do you have a positive number or not?
Negative.
Dylan, 1 over 4, 0.25, minus 1 over 16, 0.0625. You have 0.25 minus 0.0625.
Positive.
Positive. Okay. This portion is always going to be positive. There's a negative sign out here because of the fact that we know that electrons going from higher orbitals to lower ones make it an exothermic reaction. So that's why the negative is in there. And again, we're taking electrons from their original ground state. It can be the first orbital going up to the fifth. It can be the second going to the fourth, third going to the fifth. What we're doing is we're taking it, originally it's in its ground state. Once we do that though, we've taken it up, we've put energy in. Then we take the energy away. And once we take the energy away, that electron's going to go back to its ground state. When it does, it's going to give up energy. Okay. What is the frequency of light emitted from electron in the hydrogen atom going from the third energy level to the first? Men, are you up to speed here? Do you know what we're doing right now? Okay. So we got to plug numbers in here, men.
Yeah.
What is my end final? Where did the electron end? Where did it end up?
I don't remember.
Okay. I don't remember. It's a pretty good answer. Blake, looking at the problem, where are we starting from?
We're starting at the third energy level.
We're starting at the third.
From. Yep,
So,
yep.
So are we putting the 3 in where the Ni is or where the Nf is?
NF. Oh no, NI.
Ni.
Initial.
So
Yeah.
where are we ending up?
That's going to be the one over in F2, which is the first energy level.
Okay. So all we're doing to get the delta energy is we're taking a negative, we're putting in Rydberg's constant there, and we're taking that and multiplying it by 1 over 1 squared minus 1 over 3 squared. Seem fairly easy at this point?
Mm-hmm.
We have to combine that now with, we've just figured out the energy. So we're going to plug this in to our E is equal to h nu to get the frequency. Now, this is a negative number, right? We've said it's negative, but you have to understand that the negative nature is only defining whether it's endothermic or exothermic. The frequency doesn't care whether it's endothermic or exothermic. The frequency only cares about the change in the energy. So because it only thinks about the change in the energy, we have to change. We have to throw out this negative sign. In other words, basically, frequencies can't be negative. So even though this energy is a negative because it's exothermic, we have to disregard the negative sign at that point when we put it into the next equation. So we plug the energy into E is equal to h nu. We divide the energy by Planck's constant. We get a nice frequency of 2.91 e to the 15th. If we wanted to, we could change that into the wavelength by taking my speed of light, changing my speed of light. You could change it to nanometers and dividing it by the frequency, and we end up with a lambda that looks like that. This is the only problem I have. There are very few of these kind of problems that are out there. It's just hard to do many problems like this. They're all solved the same way though. Any questions on this about what I've done? Hearing crickets, I'll continue. Now, Bohr's model, you know, it worked well for about 2 years. Then they started to see, you know, this doesn't really work. For one thing, he could only get it to work for hydrogen. But the main thing is it did bring into focus the ideas that electrons can only exist in certain energy levels. And if they move to another permitted energy level, it must absorb or emit a certain packet of energy, so that there are certain energy limits between the orbitals. Interesting thing, how many of you like fireworks?
I do.
I do.
That's what we're talking about. Explains fireworks, guys. Because what they do is they put salts. If they want a red firework, a bright red firework, they'll use a lithium salt. They'll put the lithium salt into, probably they'll use lithium nitrate. For one thing, nitrate's very easily available, and for other, it goes boom too. So they put the salt into whatever firework they're doing, send it up, it explodes. When it explodes, it excites the electrons to a certain level. Then when the explosion dissipates, the energy dissipates, that energy falls back down to its ground state and makes a color. In the case of lithium, it's red. In the case of potassium, you get a violet purple color. Barium, you get a pale green. So all the fireworks, we are actually sending up heavy metals to be exploded and to be precipitated upon the population. Now, Einstein proved that waves can act like particles. Guy by the name of de Broglie came around and said, well, if waves can act like particles, can particles act like waves? And by that, what he was doing was he was trying to figure out if something the size of your body, the computer that you're looking at right now, a glass of water, he was trying to decide if big objects like that exhibited wave properties as well. And basically, he was able to find out that yes, that's true. And the relationship was that the wavelength of the particle was equal to Planck's constant divided by mv. Now, let's think about this, guys. How big is Planck's constant? (6.63 times 10 to the minus 34th. That's even
Very
12
small.
times worse than Avogadro's, right? So Planck's constant is a very small number. So in order for us to even see the wavelength, doesn't the mass times the velocity have to be a very small number? And that's indeed what he basically found out. He basically found out that you can apply this to all matter. But the wavelength associated with objects of ordinary size is so tiny that you can't observe it. And that's basically true. If you're walking around, do you observe yourself moving in a wave-like fashion? So he was able to say that he could only apply this, you can only really get wavelengths for objects the size of electrons. That's the only way you're going to be able to get something where you can actually detect a wavelength. So Einstein proved that electromagnetic radiation has particle properties. De Broglie proved that particles, even big ones, have wave properties. Which is it? Who do we believe? Do we believe Einstein or do we believe de Broglie?
Both.
Which model do we use, guys? Like the old guy who's asked what type of underwear he has on. He's going to reply. It depends, guys. It depends. If the size of the object is comparable to the wavelength of that object, we're going to use the wave theory. If the energy is comparable to the energy of a photon, we're going to use the particle theory. And there, I want to go back to one slide. There are different properties that one theory can explain, but the other one can't. And there are some things that the one can and the other won't. Interference of wavelengths. In other words, if you throw two pebbles into a pond, okay, there are some times when the waves are acting in accord with one another and the wave actually becomes bigger. But there are some times when the trough of the one wave hits the crest of the other and they kind of cancel out. Wave theory works for that, particle doesn't. Diffraction of light. If you're looking at something that light gets bent, wave theory works, particle doesn't. Polarization of light, that light can be reacted upon through filters so that you are able to just limit the wavelength of light to one plane. Wave works, particle doesn't. On the other hand, the particle works for the photoelectric effect and it works for the spectroscopy we've described. So we really have to look at these last two statements. It really is going to depend upon what we're looking at, which theory we're going to use. If we think about this mental experiment, if we have an electron that can go through two different slits, the particle nature will tell us which slit the electron can go through. But the particle nature will not allow you to look at the interference pattern that gets observed. On the other hand, if we're able to see the interference pattern, we can't determine which slit the electron passed through. In other words, the more we know about one of the properties, the less we know about the other. The velocity of an electron is related to its wave nature. Position related to its particle nature. And that led us to a guy by the name of Walter Heisenberg. Anybody ever watch Breaking Bad?
Yeah.
You recognize the name then? Basically, Heisenberg came out and said, the more we know about where the electron is, the less we know about its velocity. The more we know about the velocity, the less we know about its position. Because what he's related it to is we have a constant h, Planck's constant, we have pi and we have 4. This side of the equation is a constant. So if we really know what the velocity is, then the change in velocity, the difference in velocity is very, very small. If this is very, very small, then this is very, very large. If we really know where the position is, then the possibilities of where it is are very, very small, whereas the velocity is very, very huge. The more we know of one, the less we know of the other. And in certain cases, if we're really looking at this, we don't know where the electron is in regard to even where it's located on the atom. The electron can be further away from the atom than the size of the atom itself. A particle has position but no momentum. The wavelength is too small to measure. On the other, the wave has momentum but no position. It has a good chance to be in many positions. So what we need to do is we need to combine these two theories. We need to combine waves and particles. And the way we're going to do it is we're going to make a graph. And we're going to make that graph with waves, but those waves are only going to be in a small area. To do this, we must give the wave different wavelengths. Remember, when we combine waves, when they line up, when the amplitudes are lined up, we make a bigger wave. When we react a crest of a wave with a trough, they cancel out. So where they line up, we're going to get a bigger peak. Where they don't line up, we're going to get no peak eventually. So what we're going to do is we're going to take a small, little tiny box. And we're going to have regions in it where we have waves and no waves at all, because we've got waves in there of different wavelengths. Some of them are going to be constructive areas. Some of them are going to be destructive areas. So we got areas where we have a whole lot of possibility of the wave being there, and we have areas where there's no possibility of the wave being there. Again, this is in a small box. We've just created a quantum object. But to do this, we have sacrificed position and momentum. Our position is defined by how big our box is. Our momentum is defined by how many waves we have within that box, which led Schrodinger to develop his cat analogy. And the whole cat analogy is this. He proposed that you put a cat in a box with a bomb. The bomb has a 50% chance of going off. You seal the box up. The cat has a 50% chance that it is alive. It also has a 50% chance that it's dead. So until you open the box, the cat is both alive and dead. It's only the act of opening the box that you can discern whether the cat is alive or dead. And what he proposed, the analogy of this, is meant to kind of relate that if we're dealing with the quantum mechanics, we can't transpose the minuteness of the quantum mechanics to the macro world. So in other words, we can't say where the electron is and how fast it's moving based upon where we're at in this reality. So we're going to get into Schrodinger's equation a little bit, not much, just a little bit. From Heisenberg, we know that we can't know exactly the momentum or the position of the electron. But what we do know is we do know they have energy levels, and we do know what the wave function is. The wave function will lead us to where the electron is likely to be. Schrodinger starts off with this equation. The V times the University of Indiana symbol. That's a Greek psi, okay? The pitchfork is a Greek psi. The psi stands for the wave function. And V, I believe, stands for velocity. Not certain. I'm sorry. Right now, I don't remember what V stands for. But this is the potential energy of the system. This whole big thing here is the kinetic energy of the system. And the whole thing, the whole energy times psi is equal to the kinetic energy plus the potential energy. Now, if we're dealing with just the kinetic energy, we have to realize H is a constant, pi is a constant, 2 is a constant, the mass of the electron is a constant, and the size of our box, the length of our box, is a constant. N changes. N changes, but N changes only in whole number amounts. So basically what Schrodinger is saying here is what Bohr said. The energy is going to be equal to a number that's based on constants times a whole number value. Have I lost all of you yet?
Kind of.
Ian, I'm going to tell you to go back and look at that video by the cute girl. Try and look at it from her perspective. You may understand it a little more than that. Okay? But bottom line, all I want you to understand from this is Schrodinger was able to solve his equation so that he got his energy equal to a bunch of constants times an n value. The n stands for the states of the electrons, the energy levels that the electrons are allowed to have. Since n is equal to a whole number, the energy levels are whole number multiples of that. But where is the electron? We've solved for its momentum. Where is it? That's where the funky looking and show.
So is E the momentum in that equation?
Is what?
Is E the momentum in the equation?
It's the energy. And energy can be related to momentum.
Okay.
Okay. Now, we've figured out the momentum because we figured out basically E. But remember, we have this little funky looking pitchfork in here. That is called a psi. That corresponds to a wave function. The wave function is going to give the graph of the wave. If you square it, squaring the wave function gives you the probability of where the electron is. And I just wanted to point out this photograph. This photograph is made of probably some of the most famous scientists of all time. Basically, Madame Curie, Einstein, Schrodinger. Who else is in here? Planck. Anyway, it's the greatest collection of scientists met in Solvay in 1927. Anyway, just a short little diversion. What you have to understand is that you can never know precisely where an electron is and know its momentum, but we can do a statistical analysis. What Schrodinger did with his equation is he mathematically treated this so that we are both incorporating wave and particle matter. And eventually, his equation gets solved to the point where it is H psi is equal to E psi, where H is a mathematical function and E is the total energy of the electron. If we plot psi squared, that gives us the probability distribution of the electron. And this is how it's properly drawn. Do you notice how it's really, really intense in the center? And as we go out, the little blue things kind of fade away a little bit. That is because we're showing that the density is greatest closer to the center, and it dissipates the further you go out. If you solve Schrodinger's equation, you solve it for 4 quantum numbers. The first one is called the principal quantum number, and that tells you the size of the orbital. Basically, it's what you know as shells. We also solve it for the angular momentum, L. That will tell you the orbital shape. We define it in terms of the magnetic quantum number, M sub L. This specifies orientation along specific axes. And the last one is called the electronic spin quantum number. That gives you the direction of the electron spin. Solving the wave equation will give you a set of wave functions or orbitals and their corresponding energies. The electron, it's in an orbital, will be described by 4 quantum numbers. The first one, N, describes the energy level on which the orbital resides. N can have values of whole numbers greater than 0, cannot be 0. As a matter of fact, if we're looking at the periodic table, the values of N can be 1, 2, 3, 4, 5, 6, 7. We only have 7 values in the periodic table, because if you look down the left side of the periodic table, we only have 7 rows. The other thing is, as N becomes larger, the electron is further and further away from the nucleus. The Azimuthal quantum number, or the angular quantum number, what this defines is it defines the shape of the orbital. The allowed values are n minus 1 through to 0, back up to n plus 1. In other words, if L is equal to 1, I'm sorry, if n is equal to 2, we can have 2 minus 1, a negative 1, a 0, or a positive 1. It goes 0, fans out, both in positive and negative direction, until we reach n minus 1. We can also use letter designations, and these are the things you're familiar with. We can use letters to designate the value of L. And now we're back into familiar territory for you. If my L value is 0, I'm dealing with an S. If my L is 1, I'm dealing with a p-type orbital. 2 is D. 3 is F. If my L is 0, that means I'm dealing with an S orbital. S's are spherical in shape, and the radius increases as my N value goes up. Yeah. All right. Now, remember I told you we had constructive interference in which the wave got higher, and we had destructive interference that the wave went to 0. Do you remember that? Guys, do you
Yeah.
remember that?
Yes.
So those are called nodes, and an electron cannot exist in a node. So if I'm dealing with my S value, my 1s, I have a node at the very origin because the electron cannot be in the nucleus, but it can be anywhere else. If I have a 2s, that 2s electron can't be in the space between the 1s and the 2s, and it can't be in the origin. 3s, that electron cannot be in the space between the 2s and 3s, or the 1s and the 2s, or the origin. So bottom line, a node is a region in which there is no probability that the electron exists. At the node, psi squared is equal to 0. For an s orbital, the number of nodes is going to be n minus 1. And basically, guys, we are talking about the spaces between the orbitals. If we want to look at it being plotted out as a term of probability, if we have an S, there are no nodes in the S orbitals. It can't exist at the origin, so that's the only place where the probability is absolutely 0. If I have a 2s, I have one node. That one node occurs in a space between the 1s and the 2s. It also cannot exist at the origin, but other than that, it can exist pretty much anywhere else. 3s, same thing. If I have an L value of 1, I have a p orbital. A p orbital has two loads with a node between them. The node is where the electron cannot be. What you see on the left is a better example of what a p orbital looks like, but you'll see them drawn out as looking like a balloon that's been squeezed in the middle. The p orbitals exist on the z, x, and y axes. Again, as n increases, the value of the space that the electron occupies gets bigger. All p orbitals have a node at the nucleus. D orbitals, it's like squeezing the balloon twice. I got 4 lobes, and the lobes are located along planes. This top one is along the YZ plane. This one's the XZ plane. This is on the XY plane. And this is on the XY plane, but the lobes are actually going through the axes. And there's a 5th looking one that looks like a p orbital with a donut around the center. F orbitals take this shape. We're going to the 3rd quantum number. The third quantum number can have values minus L through 0 to plus L. So if we have a 1s orbital, remember the L value is n minus 1. So if I'm in the 1, I cannot have any other value for L other than 0. And if L is 0, m sub L also has to be 0. If I have a p orbital, my values of m sub L can be minus 1, 0, and plus 1. I have 3 p values because my L is 1 for a p orbital. D, the value of L is 2. I can have 5 orbitals for D. Minus 2, minus 1, 0, plus 1, plus 2. F, L value is 3. M sub L values can be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Are we pretty good on the magnetic quantum number?
I think so.
This slide basically gives you what's possible, the quantum numbers that are possible for n, L, and m sub L. Fourth one's the easy one. Basically, electrons have spin. And there are 2 possible directions of spin. You can go clockwise, you can go counterclockwise. So the allowed values are plus a half or minus a half. Basically, through a mathematical study, they figured out that no 2 electrons can have the same exact energy. Because of this, they had to impart a spin quantum number so that one were spinning with the magnet, the other were spinning against the flow of the magnet. So, reviewing, the principal quantum number, n, can be whole numbers, not 0. Anything from 1 to 7, whole numbers. It indicates the size of the orbital. It's the rho, if you want to think of it in that fashion. The angular momentum dictates the shape of the orbital. If L is 0, it can be S. If L is 1, it's P. If L is 2, it's D. If L is 3, it's F. L values can be n minus 1 down to 0. So if I am dealing with the first shell, n equals 1, the only possible value for L is 0 because it's n minus 1 down to 0. If I'm dealing with the second, n equals 2, that allows me to have n minus 1, 1 or 0. If I am dealing with n equals 3, this allows for L2, L1, L0. So it's not until I get to the third shell that I'm able to have d orbitals. Again, if n is equal to 4, I can have L is equal to 3, 2, 1, or 0. So that's why the f orbitals don't appear until the fourth shell. Now, we have our M sub L, and the M sub L indicates the orbital orientation. If you want to think of it like organizing it on the X, Y, and Z axis planes. The permittable values for M sub L are minus L through to 0 up to plus L. So if L is 2, the permissible values for M sub L are minus 2, minus 1, 0, plus 1, plus 2. Last one is the easy one, M sub S. It just tells you the direction of the electron spin. It's either going one way or the other, and it's designated by either a plus a half or a minus a half. Blake, is A possible? Is it possible to have those 4 quantum numbers? Blake, you eating dinner?
Oh, no, sorry. I thought I unmuted. Yes.
Okay. Is it possible for n to be equal to 1?
Not if L is
What
1.
were my rules for n?
Yeah, N is, well, L is N minus 1, right?
I'm
So they
sorry?
can't be the same.
There you go.
So I don't, yeah, I don't think they can. Yeah.
No. N can be 1 because n has to be a whole number and it can't be 0. So n can be 1.
Hmm.
Trouble with this is that L can only be n minus 1 down to 0 whole numbers. If n is 1, L can't be 1.
Yep.
If L is 1, M sub L certainly can be 0, and the spin can be plus a half.
Gotcha.
Okay, Ian, what about 2? Is this set of quantum numbers good?
I would say no, but truthfully, I'm not 100% on my answer.
Okay. Is it possible for the principal number to be 2?
Yes.
Okay. Whole number between 1 and 7. That's good. Okay. L. L is equal to n minus 1 whole numbers down to 0. So can L be 0 if n is 2?
No.
L values can be n minus 1 down to 0, including 0. So
Okay.
is it
So yes.
possible? So it's possible for L to be 0 if the n value is 2. Think of it another way, Ian.
Hmm.
Doesn't L being 0, doesn't that stand to be like an s orbital?
Yes.
So is it possible to have a 2s orbital?
Yes.
So it's a good number. Likewise, if we look at these two, right? The L value of 1 stands for a p. Can we have a 1p orbital? Think about it. The first shell is just hydrogen and helium. Are there any p orbitals in the first shell?
Yes.
Look at a periodic table, Ian. The first row consists of only hydrogen and helium. Are there any p electrons in the
No.
first shell? Because the p orbital can't exist. Okay?
Got it.
All right, men. Men? Come on, man. Okay, I'll leave him alone. Dylan, can the principal quantum number be 3?
Yes.
If the principal quantum number is 3, can the L value be 2? In other words, if I have a principal number, a shell 3, can I have a 3D orbital?
Yes.
Yes, you can. That's the first row of transitions, are 3Ds, all right? The other way you look at this, L can have values of n minus 1, whole numbers down to 0. So if n is equal to 3, L can be 2, 1, or 0. Is that good?
Yeah.
All right. Angular momentum, minus L through 0 to plus L. Is this a good quantum number for that?
Yes.
Yep. What about the bottom one?
Yeah.
So this C is a set of good quantum numbers. And ladies and gentlemen, that is my last slide. And we are a little bit over. Any questions about what we've been through tonight? I would strongly, strongly suggest finding the videos for Heisenberg and Schrodinger. The Schrodinger one especially, because the girl is quite cute and she's funny. It'll take, both of those will probably take a half an hour out of your lives. They're good. That's what I used to prepare. Well, maybe that's not such a good advertisement, but that's what I used to help prepare me to go through this PowerPoint. If there's nothing else, guys, what we're going to do next is we're going to go back through and relearn configurations, orbital diagrams, and when I give you a set of rules for the quantum numbers, you're going to be able to tell me what element it is. And if I give you an element, you're going to give me the quantum numbers of the last electron going in. If that's it, gentlemen, y'all have a nice weekend.
Thank you. You too, Professor.
Thanks, Professor. You too.
Take care.
See ya.
Man, are you doing okay? Man, have you gone off to have lunch, dinner? Bye, man.